week is the fall reading week, so uh, we won't be meeting next week. Won't be meeting here next week. I'll welcome email, of course. Everyone get my email yesterday? Good. So I'm hoping that the remaining point we haven't gone into concerning Pascal's triangle, the multiplicativity of extreme points, extreme states. The state being a unital ring. Well, ring is supposed to be unital. We say a unital ordered ring, and the unit of the ring is also it's called an order unit. Some integral multiple, some positive integral multiple that majorizes anything in the ordered group. So the polynomials of the Pascal ordering, the monomials in x and 1 minus x being positive, generating the positive cone. These so positive functional means positive on each of those. And by the way, we've seen how that fits into the Hausdorff moment problem. That these positive numbers down the left-hand side of the Pascal's triangle, when you fill in the whole triangle with numbers at every point, positive, well, not necessarily a priori, not necessarily positive numbers, but if they all are positive, this corresponds to the all the higher order derivatives, discrete derivatives being positive, right? And that's if you can actually construct a measure that has those moments, then finish. That's the Hausdorff moment theorem. And, how do you get such a measure? Well, you have a positive functional already, and that's what a measure is, right? The positive functional on continuous function under if it's a compact Hausdorff space like the closed unit interval. The positive functional on the real value continuous function, then there's a theorem. If it's not the definition of a measure, then there's a theorem that says that one of the two Reese representations here. Okay, so but it's only defined on polynomials so far, and it's not pointwise positive a priori. It's just positive on these monomials, which of course are positive on the interval 0, 1, strictly positive on the interior. So it turns out that strictly positive on the interior for a polynomial is exactly what this what the Pascal order relation is, and it's to prove that we need the calculate the extreme point of the positive function, and then we use that to prove that something was strictly positive in the interior of the interval, and it was in a sum of monomials in 1 minus x. So intervals, positive intervals combination. So to calculate the extreme points, extreme positive functional, we well, you can do it immediately if you know they're multiplicative. If you know they're multiplicative, then on the monomial, you need to, so by the way, if you take x, then x lies between 0 and 1, and so a positive functional will lie between 0 and 1 on x, because at least the state, because it's equal to 1 on 1 and 0 on 0, and on x it lies in between those, so it takes on some value of the interval 0, 1. If you know it's multiplicative, and it takes 1 minus that value on 1 minus that. And if you know it's multiplicative, then you know what it is on all monomials in x and 1 minus x. And that's positive. So that was an important step in the proof that the two order relations are the same. It's needed to show that the state on the triangle order is continuous. It's bounded functional on polynomials on the interval 0, 1 with the soup one. Which means that if the polynomials, you know the polynomials are dense and continuous functions, then it tends to cause the functional and continuous functions in the pointwise order. Well, okay, so there's this. How many people got a chance to look at the question of proving multiplicativity? Well, that's not so many. Well, okay, so let's take a look at it now. You're assuming it's an extreme point. So suppose that phi from zx a group of polynomials, the Pascal Wedding, positive function. You have a positive element, then phi of that element is positive. And let's say it's a state phi of 1 equals 1 because it's we want to talk about extreme points, and it shouldn't just be all functionals because if every positive multiple, every positive scalar multiple of a functional is positive, and the set of positive things is not going to have very many extreme points. But so I guess so. Are there any extreme points? If you have a cone, are there any extreme points? Or what you might call extreme rays, but I don't think there are any extreme points, right? Well, the apex, the point of the cone might or might not be an extreme point, right? Depending on how acute the cone is, how sharp it is. We're not interested in zero. So that's why what you do is you cut the cone across, and if if it's functional, then a good way to cut it across is to say we'll look at functionals that are equal to 1 on 1, and we know that every no non-zero positive functional is equal to 0 on 1 because 1 is an order unit. That's an exercise. Okay. So if we look at all positive functions, well, no one really, maybe Victoria, no one really says we have to look at all positive functions. And I guess, well, this whole business, this whole long business of the Hausdorff moment problem, this is a very good subject for an essay. I would recommend it as essay 1 or essay 2. don't have to actually go through all the details of all the proofs, but maybe organize things enough so you know what the different steps are, so that the reader knows what the different steps are and what has to be proved. Okay, but you want to know, so you look at the states, okay? The state. And so we want to know if the phi extreme well, if we're going to calculate the extreme point, I guess we want to know its equivalent to being multiplicative, right? Because if we have an extreme point, then knowing it's multiplicative helps you find out what the functional is. It's got valuation at some point on the interval, right? Considering you consider the polynomials and functions on the interval and evaluations on the function. That's a positive function. Pascal would. Anything, all the monomials are pointwise positive. But conversely, if you want to know what you want to know what all the extreme points are, I guess we want to be able to see that the evaluations at points on the closed interval are extreme points, right? So we want to know if only if multiplicative. Okay, that's with respect to the product of polynomials, multiplication of polynomials on the one hand, and multiplication of real numbers on the other. Okay, so that's what the exercise, that's what the remaining step is. The trick to the proof is to know, because we want to assume string, okay? Suppose that A and B, that A, a positive A, maybe positive and less than or equal to 1. The, B, the, given X, okay? What's the trick? The trick is to let A be fixed and let B vary, okay? Has anyone ever seen that happen before? Sometimes when you're calculating limits for a product, you might fix one of the variables and let the other one go to the limit, right? Which is similar to that. It's just algebraic. So what we want to do is write phi sub A for the functional B goes to phi of AB, okay? B is arbitrary in the group, in the ring, and A is fixed. So this is a functional, okay? And it's a positive function because B is positive, well, A is positive, then A times B is positive, because that's what happens in an ordered ring. So this is a positive function. And phi sub A of 1 we want to prove that is this well phi sub a is not a state because phi a of 1 is equal to phi a. Okay, but by the way, what I'm doing is what everyone should be doing right this morning or last night, right? This is how you approach the point. You don't have any idea what to do, but you just go ahead anyway. Okay, so that's what I think that's what you do in a lot of areas, as long as it's reasonably safe. If you're, like if I'm standing in front of a large class, maybe that's not what I should do. But I can say that the reason I'm doing it is to set an example, right? So now, suppose if phi a, suppose phi a happened to be 0. Well, then they will have to worry about that later, right? So the point is, I want to consider first the case that phi of a is not equal to 0. So hold on, a is a polynomial, and phi of a is a number. Now, of course, a might be 0. A might be 0. But in that case, AB is always 0 too. And so you have multiplicativity very equal. Okay? Phi of AB is 0, because AB is 0. And phi of A times phi of B is also 0, because phi of A is 0 and phi of A is 0. So it's not quite so simple. You'd have to prove that if phi of A is 0, then phi of A times B is 0. Okay? That's what let's say that's another day. Okay? The point is that if phi of A is phi of A is not equal to 0, then phi sub A divided by phi of A is a state. Okay. But phi being evaluated on 1, you get phi of A divided by phi of A. And furthermore, suppose you look at the phi of B. So A plus 1 minus A. So notice that 1 minus A is also positive. So we can do the same thing for 1 minus A. All right. And phi of B is equal to phi of A times phi sub A, phi sub A of B, plus phi of 1 minus A divided times phi sub 1 minus A. So of course we have to we also assume so we assume that phi of A is not equal to 1. The same for so the arithmetic is that the phi of B well, it's phi of A here. Yeah. phi of AB is phi sub A of B, and that's what this first term is. Oh no, phi of B is the sum of two things. First thing is phi of AB. Oh, it's phi of AB. That's phi of AB, and this is phi of quantity 1 minus A. And if you add them, you're A plus 1 minus A. Right. So well, that's just checking. That's just checking that that's true. Okay, phi of B is an average. If phi of A plus phi of 1 minus A is equal to 1, both positive and equal to 1. So it's we're getting a convex combination. We're getting what's called it's an average. It's an average of phi A and phi 1 minus A. So phi is an average of phi A and phi 1 minus A. Phi is an average of phi is an average of phi sub A and phi sub 1 minus. But that means that if phi is extreme, then if you have an average, then it's equal to the endpoints. You know, there are no non-trivial averages, yes?
But we don't know that phi sub A is a trace or is a state. Phi sub A might not be a state.
No. Well, we're talking about states, right? It means positive functionals on the ordered group, on the ring, which are normalized. So phi sub A is also a functional. Now it's not a state, but you divide it by phi of A, then you get a state. And so then you're multiplying that state by this.
Oh, I see.
So you're averaging two states.
I see.
You're averaging two states. And so if that is an extreme point, then that means that it's trivial average. Okay. So well, at some point I'd like to leave it open again. So phi extreme. Phi is phi is at phi sub A. What are the two things you're averaging? Well, phi sub A was okay. So actually, I should have divided here by phi and A, right? Well, it's going to take long, okay? But do you see? Does everyone see the idea? So, what I hope is that you have enough time over the weekend, you know, and even without dipping into next week, to check out that this thing is we're not finished yet, but at least phi extreme can be the same that phi A over phi of A is equal to on B is equal to phi AB. So okay, good. Okay. So I'm hopelessly mixed up now, okay? But I think that this is what students, the fairly advanced students, should get a chance to see. They should get a chance to see someone get mixed up and have a chance to figure it out. Because definitely this is a solvable problem, right? So okay, so we can take it up after the break. After the meeting. Okay, well, there was another place where I didn't finish the proof. Okay. Now, if I were if you people weren't so advanced and weren't such good students, so you can see what's going on, then maybe I would try to fake it and say I'm doing this on purpose. Okay. And who knows? Maybe I'm just very modest, and anyway I am. Okay. But very tactful. But there was exactly another point, and that was looking at the, you can see I got saved by the bell, but it was okay, so we had the two projections because we have K0 and the extension. K0 and y0. And we want to show that this is exact, okay? It means you have something in the kernel, so in the class of E and F are A is unital. So we define K0 by looking at projections to begin with. Well, or in the matrix algebras, and then it's not even until you join a unit, and then you map onto the so if there is a unit. Is there a place here where it's an extra batteries? Right?
We'll make sure to do that next time.
Good. Thank you. Because there are people on the project. So this not special class. Class of B minus class of F. E and F are projections in the algebra A because that's when the algebra has a unit. Okay, thank you. When the algebra has a unit, that's how we define K0. Just like that's how you define them. Given the natural numbers, counting numbers, called in grade 2 maybe, to get the integers, takeaway numbers. You look at pairs of natural numbers. That's one way to do it. And then you imagine 4 take away 2, or that's the same as 6 take away 4. So you look at all those pairs where the difference is 2. And that's, you don't have any way of writing, you don't have any way of writing, you have to have a motion. But you don't have a formal definition, maybe. So the formal definition would be just to look at all the pairs. The difference is the same, which you get by saying the difference between two pairs is the same. That's expressed just by using addition, right? You just move things to the other side of the equation. So that's and it's the same here. The formal group is got by from the semi-group is got by taking pairs of things in a semi-group of equivalence classes, and then you want to wonder when the difference should be considered the same. Well, that's defined in terms of the semigroup operation of addition, right? You just what that means is that the E and the F are not unique. So the trick that I forgot is at the very, very beginning, you use, this is probably everyone has seen this. Maybe I'll bet everyone has seen this, or most of you have seen it. When you look at a pair of projections to represent the K-class, you can always assume that one of them is the unit, or the unit of some matrix algebra. Because it's always going to be less than or equal, that projection is always going to be less than or equal to the unit in some matrix algebra. And so that you look at the difference, and you add it, you get the unit, and you add that same thing to the other projection. And that's just like going from a pair of 4, 2 to 6, 4. You add 2 to each side. Okay? So that's, but then I can just change the notation. I can assume that F is equal to 1. But that's, now I shouldn't have to say anything. Because what we want to do is find this, we want both E and F to belong to I tilde, right? We've got by considering I, which is contained in A, and adjoining the unit, okay? I tilde or a matrix algebra over I tilde, okay? And that's what we want E and F to be, because that's how you get K0 of I, right? And what we did do is reduced already, without even remembering that the F could be a Chipson the unit. We reduced to the case that E minus F, E is equal to F modulo the ideal. And what we want is both of them should be in the ideal. Well, not exactly in the ideal, but the unit adjoining. But it says that, okay, how many people can finish the argument with one line finish to the argument? Abigail? We want F, both E and F, to be in I tilde. And of course, by definition, the unit is in I tilde, or also for matrix algebra. And so, so we have F belongs to I tilde. Okay. And notice that so E minus F belongs to I. And of course, I is contained in I tilde, right? So how many people can finish the proof? It's a half a line now. No hands. Okay, there's one. There's one. There we go.
Because we have that F is an I tilde,
I can't quite hear you.
because E minus F is an I tilde and F is an I tilde. So
Yes.
it must be an I tilde.
Yes. You just have to be able to, speaking of addition and subtraction, that's what that's what this is talking about, right? Yeah, good. Okay, well, that's that's, by the way, we have exactness here now, and also for K1, because if we follow this other, the slightly unwieldy proof I gave, K1 is just K0 of suspension. No, that's not what periodicity, it's true for real scalars too. But then, but by the way, if suppose we looked at the definition of K1 in terms of invertibles or unitary, in fact, and then try to prove half classes. Maybe it should be called 1/3 exactly. But it turns out that it's, for K1 defined that way, it's easier than for K0. Okay? Anyone taking a look at it? Well, let's take a look at it now. Suppose we have a unitary element of A. So we're K1 and A. Suppose it maps into the course. That means it's connected, okay? Connected to the unit in some matrix algebra. But that means that we've already mentioned this in the Pascal triangle setting. No, sorry, we mentioned it in proving that we reduce the case. We didn't prove it. I stated it. I said there's something. The unitary is in the connected component of the identity, and it's a finite product of exponentials. Okay, exponentials of 2 pi I times self-adjoint. Of course, you don't need to say there's no projection around, so you don't need to say 2 pi I. Okay, but you need to say I. Take I times the self-adjoint, then the exponential of that is unitary. And if it's just an organic algebra, complex organic algebra, then you can still exponentiate E times any element. You don't need the I. Well, this is true for a real organic algebra too. So you don't need the I. Any element you can exponentiate, right? And but the point is that you have a finite product of exponentials. Each exponential comes from upstairs. Okay, so we have a unitary, a vertical element in A, and downstairs it's a finite product of exponentials. But if we lift those, then those exponentials are in the image of exponentials up here, right? So we take, and those are connected to the unit. So we take the unit, the original invertible element, and wipe off the exponentials. Because what's so in effect, it's K1 class. We can suppose that the original invertible element maps into the unit, exactly into the unit, because the exponentials don't cut any ice at all. That's still an expression. 50 years ago, it was an expression. I guess not too long ago, I mean, not too much longer ago than 50 years, people had ice boxes. They didn't have refrigerators that you plug in. They often had ice boxes. I think we always had a refrigerator. But in the town where I grew up, there was an ice house where ice was cut from the river, from the river, and packed in sawdust, and they're there all year round. I remember finding it once. I think I dug away in the sawdust to find the ice. I didn't know what it was for, but I hope I covered it up afterwards. Okay, but so cutting ice means cutting it for the winter, right? Okay. And it wasn't just in this town that happened to be on the river and had thick ice. Ice had ice everywhere. Well, okay, so if we have a unitary that maps to the unit, then it already belongs to I tilde, and we're finished. Okay? Okay. So it uses part of the proof, one small part of the proof, A0 theorem. But that's it. And that's, okay, so that's an exercise to think about. You have a vertical element of a valid algebra with unit. Of course, so the inverse makes sense in the algebra. And it's a finite, and it's connected to it's connected by a path of invertible elements to the unit. You can always talk about, for this exercise, talk about unitaries if you want to. Well, except you have to be real careful. To get to block periodicity, as I said, it's going to be going to work some of the time in panic algebra. Okay, but the point is that the connection component of the unit. Actually, this is the connection component. Yes. Do you have a question? Oh, okay. Anyone have a question? Yes, yeah. By the way, let me just interrupt. I think at any moment, everyone should have at least one question, okay? So if I ask if you have a question, then you can, you don't have to just sit there, okay? Because I have questions. You ask me if I have a question, I'll bet you I could, actually at the moment I might be at a bit of a loss, okay? All right, yes, go ahead.
I was thinking about that last question that Scott.
Right.
I was thinking about the above question, the last
Oh,
question.
the states.
Yes, yes, yes. I was thinking about.
Can you show that the three difference one question?
Yeah,
good.
I want to say if I'm thinking right. I think that the same method that you use for ZX, we should do it for ZX2 and then all down. Yes.
Well,
For example, I think if it is right for ZX2, it will be a 1 minus a and a multiplied a times 1 minus a. Do it work like this? Do you mean this?
What you have to prove is that phi sub a. What you have to prove is it's equal to phi of a is equal to phi of a times phi. Okay,
Yes.
that's what you want to prove.
Yes, for the phi in ZX.
Right?
For the phi in ZX. Yeah, Z of X. Yeah. For the phi in Z of X2,
Okay,
we can do the same thing.
It sounds good, but why don't you send me, or even better still, send everyone an email?
Yeah.
You have the list. I think you have a nice little group. It shouldn't be no more than a few lines. It could be just a few lines. Okay.
Yeah.
Then if you know how to do it, then just broadcast it on your same
That you want us to do the same thing. Do it for ZX and then for ZX2 and
I'm not sure
for
what you mean.
ZX to
What's
the power
this
n.
X2? What's this X2?
I thought that in this Brattle diagram, now we are somehow between the level 1 and 1 minus 6.
Yeah.
Yes, and then we go, for example, for the level
Okay.
2 to the 3.
Yes, right. But you know, at the moment we're just talking about a general ordered ring.
Yeah.
There is the Brattle diagram is a special case, and I don't know if that's going to help to consider the Brattle diagram. It's some more for the unit. It's one to measurize anything. So it is an application. Used to forget about the graph. Yes.
Well,
Please remind me of your name.
Jalal.
Jalal, okay.
Yeah. The exactness, but in the case for K1, how did you reach the point where you said that unitary maps to a unit and then we concluded, but what was the step leading up to that?
Okay, we want to prove exactness, right, in the
Yeah.
middle. It's called half exactness for the whole thing. All right. Well, so you speak to algebra, you have a unitary. And K1 class maps to K1 of the quotient. So the unit, you take the class of the unitary and the quotient. We're assuming that's 0 in the K1 group. Which means if the unitary is connected, that's the definition. The unitary is connected component of the of the unit of the quotient algebra. These have to be what it makes. Okay? And but you'll go 2 by 2 matrices, but the unitary in the upper left-hand corner, and put 1 in the lower right-hand corner. And compare that to 1, 0, 0, 1. Could be that equal to the other for some higher one. Okay, the point is that we have a zeta algebra and the unitary, and a path of unitary to the unit. So that unitary must be a finite product of exponentials. This is the IH, e to the IH1, e to the IH2, and so on. And each one of those lists to a unitary upstairs, which is also connected to 1. This, by the way, the exponential is trivially connected to 1, because we just turn off and multiply the going on by the t between starting at 1 and going down to 0. That gives you a continuous path. So once you got these exponentials upstairs, they're in the connected component. So if you multiply them by the inverses of them, we'll get rid of them. When you pass to the quotient, all you get is the unit. And then that says that the unitary upstairs it's already exactly where you want it. To find K1 is the ideal. In the image of K1. Well, that's that's a good question. And that's you want to keep reviewing things like that. That's how you review a proof. Well, everyone knows that. The question is, do people know that you have to do it in real time? Right? That's what advanced students. That's what I think advanced students learn how to do this reviewing in real time, or to do it 5 minutes later after the class, or then later in the day. Or, yeah, okay. Okay, but so now we're getting the next thing to talk about, not next week, but the week after, is what happens in the complex scalar case when we try to prove that, well, I guess we should be, we can already be talking about the index map K1 of the quotient, K0 of the ideal, which makes this, which is exact at the 2 ends of that arrow. We could talk about that before we concentrate on the complex case. That's called the even index map. And the odd index map, which we've already defined, we've got some map. We have without not any trace of exactness. And that's we're going to have to. Well, that takes some serious work. Okay, but periodicity is one of the theorems of the 20th century, and that's my guess is that weighed heavily in how Bach distinguished among all 1 year he was distinguished among all American scientists, or even which we can share in the glory of because he came from here. Well, he came from Czechoslovakia a long time earlier. It was a substantial part of his education here.